Yeah, let's get down to it then for today. So we are still talking about gerrymandering, and our topic for today is called the efficiency gap. Efficiency gap. This is a statistical measure of packing. The idea is you can use the efficiency gap to measure if the districts have been packed or not. And this is a way of sort of mathematically detecting an unfair gerrymandered map. It is a statistical measure of packing. Remember, packing is when you sort of pack a district full of members of one party, and you let them win that one, but because you pack them all in, they have a hard time winning any of the others. That's the idea behind packing. And you can actually measure this sort of statistically by just sort of counting how many people are overloaded in certain ways. So that's what we're going to talk about, how to do the efficiency gap today. The final answer is like a number, a specific percentage that says the districts are packed in favor of this side or that side to this this percentage amount. It's all about, and this is the basic concept that we're going to have to talk a little bit about. It's all about counting what we call wasted votes. The purpose of packing, like if I pack one region full of a certain party, the reason you do that is so that they can win that district, but then their votes have all been taken up by winning that district, and so they're going to lose all the other ones. We say those were wasted votes. That's why they're called wasted, because you didn't really need them. You didn't really need so many to win that one district that you packed them into. The purpose is you pack them in so that most of those votes just kind of disappear because they were way above the threshold to win. Those are called wasted votes. And here's a very specific definition here of what counts as a wasted vote. So a wasted vote is just one which doesn't contribute to winning the district. So a wasted vote is any vote which doesn't contribute to the win. I will say to the winners win. All right. What I mean by that is any vote, first of all, any vote for the loser counts as wasted, because that's not a vote that is contributing to a win. So any vote for the loser counts as wasted. And also, some of the votes for the winner count as wasted. So any vote for the winner beyond the threshold, like extra votes for the winner that they didn't actually need, just like they got more than they needed. Any vote for the winner beyond the threshold counts as wasted. All right. This is the definition of a wasted vote. This is really the important part that you need to remember. Any vote for the loser is wasted, and any vote for the winner beyond the threshold is wasted. And it turns out if you pack the districts in an unnatural way, then one of the parties will waste far more than the other. So for example, here's a typical example. In a district, let's say with 100 voters, let's imagine the D's and the R's are my two political parties. In a district with 100 voters, if they vote like so, if it was something like D's are 47 and the R's are 53, this is not packed. They are fairly evenly matched in this district, so there's no packing going on. And who is wasting votes in this case? Well, first of all, you have to decide who the winner is, and it's the R here. R is the winner. And I said, if you look at the top there, any vote for the loser counts. Any vote for the loser counts as wasted. So I'm going to try to just count up how many votes are wasted here by each party. So in this case, any vote for the loser counts as wasted. So these are all wasted because those are all voting for the loser. So here D wasted all 47 votes. And how many did the R's waste? In this case, 53 votes for the R's. Can somebody say what's the threshold to win in this case? If there are 100 voters, how many do you need to win?
51.
Yeah, 51 is how many you need to win in this particular case. 50 would be a tie. In order to win, you need 51. And so, how many wasted here? So I would say 51 is the threshold. And the R's got 2 extra, right? And so they wasted 2. That's the way that this works. So D's wasted 2. All right? This is how you count the wasted votes. Any vote for the loser is wasted, plus any vote for the winner above the threshold is wasted. So, in this case, the loser wastes a lot more, which is what you would expect. The loser is the one who lost, so all of their votes are going to be wasted. And the winner is probably getting just a few extra, and so they don't waste a lot. And so I would say in an unpacked district, which is what this one is is fairly evenly matched between the population. So in an unpacked district, the loser wastes a lot, right? And the winner wastes a little. That's just how it works out with the numbers. Every vote for the loser is wasted, and that's typically a lot in an evenly packed district. In an unpacked district, these are evenly distributed, more or less, 47 to 53. What about if the district is packed? That means it has something like 90 D's and only 10 R's. Something like that would be packed. So if it's packed, what does that look like? Here is an extreme packed example. What if it was, say, D97 and R3? Now, who is wasting more? In this case, the D's are the winners. The threshold, again, is 51. The D's got way more than they needed, to the tune of, you do the math, I think 46 extra, all right? This is 46 extra votes beyond the threshold, which was 51. So D wasted 51. Whereas the R's, they lost, but there were only 3 votes, so the R's wasted. These are the losers. And the rule is the loser wastes all of their votes, and so R wasted 3, all right? And you can see this is very different from the previous time. Yeah, question?
What if D weighs 46 instead of 51?
Yes, 46. Sorry, I was saying the numbers as I wrote it. Thank you. 46 is what I meant to say. It's all of the votes beyond the threshold. That's this number. How many extra votes did they get? Sorry about that. So D wasted 46 and the R wasted 3. And this is very different. Remember I said in an unpacked district, the loser wastes a lot, but the winner wastes only a little. It's totally the opposite in this case. When the district is packed, the winner wastes far more than the loser. All right? So here, if it's packed, in a packed district, the winner wastes a lot. It's the opposite. The loser only a little. All right, this is the basic idea. So you can actually, just by counting up the wasted votes in each district, you can detect who's being packed and who isn't, because the amount of wasted votes is totally different in ordinary divisions versus packed divisions. And so this is the idea behind detecting packing. You count up wasted votes. And in a packed district, you expect the winner to be wasting far more than they would have otherwise. That's the idea. All right. Let's try to actually do some examples here. So I'm going to do a simple one, and then I got some for you to try, as usual. We are going to count up all the wasted votes and then just kind of make some simple percentages. It's a simple procedure, although you have to know what you're doing in order to do this. So let's try an example of the efficiency gap. I'm going to use one of the pictures that I handed out, one of the very simple ones. If you don't still have this, it's fine, because I'm not really going to use the picture very much at all, but one of these guys. So here is one of these grids, and I'm going to make districts like this. I know you probably don't have this picture on hand, but you only really have to look at the picture once at the beginning. Oops. I want it like this. All right. Like so, okay? Let's say these are 5 districts, and I will give them numbers. 1, 2, 3, 4, 5, like so. All right. What we have to do is count up in each district who won, who lost, and then how many votes were wasted by each side. So we're going to count all wasted votes per district. And this involves making sort of a big yet simple chart. All right, and here's where, if you don't have the same picture, I'm about to translate the picture into a chart anyway. So I have the districts and the darks and the lights. Eventually I'm going to add 4 more columns to this chart, so leave some space. But what I'm going to do just to get myself started is just count up the vote totals in each of my 5 districts. All right. So in District 1, what I see is 4 votes for the darks, that's the D, and 6 for the light, which is the L's. All right. In District 2, it's the same situation. 4 D's, 6 L's. In District 3, what I have is 2 dark and 8 light. 2 and 8. District 4 is all light, so that's a 0 and a 10. And District 5 is all dark, that's a 0, 10 and a 0. All right. So once you have these, this is where you look at the picture once to get all the totals down. After this, it doesn't really matter anymore. You don't have to look at the picture anymore. I mean, everything is just based on this chart. All right, so the first step is to figure out what the threshold is to win in each one. Yeah.
You said which districts to circle.
This was just a made-up example. So a typical example of this, I will show you some districts, and then I say, find me the efficiency gap of these districts.
Okay, thank you.
Yeah, the point of this whole thing is to measure basically how fair these districts are. So I will show you the districts to begin with, and you tell me, you do all this business to figure out if they are fair or not. All right? Anyway, we need to figure out the threshold to win. In this example, it's very easy, but sometimes it'll be slightly more complicated. So towards that end, first I'm going to write down the total number of votes in each district. And in this example, there are 10 every time. Usually they're going to be all the same. Now, in the real world, the different voting districts are not, they can't make them exactly the same population just because there are slight variations, but so the totals in the real world are going to be slightly different. All right, then my next column is going to be the threshold to win in each district. All right, now in this case, there are 10 voters in every district, and so what will the threshold be each time?
6.
It will be 6, yeah. 5 would be a tie, which is not good enough. You need 6 to win, so the threshold here is 6 every time. In this example, they're all the same every time. All right. And now is that is, just sort of bookkeeping. Now, this is the interesting part. The hard part, I suppose, it's not really hard. You just have to kind of make sure you know what you're doing. I'm going to count up D wasted versus L wasted. So in each district, how many D's are wasting their votes versus how many L's are wasting their votes. Now, I find it helpful each time to circle the winner, just because, like I said, how you tell whose votes are wasted has a lot to do with who the winner is. And remember, the rule is all votes for the loser count as wasted, and any votes for the winner beyond the threshold count as wasted. So in the first row, I have, first of all, the D's lost. 4 votes for the D's are all wasted. All votes for the loser are always wasted. And then for the winner, any votes beyond the threshold are wasted. Now, L's were the winner. They got 6. That is 0 beyond the threshold. So the L's have wasted 0. All right? The wasted, if you're the winner, the wasted is how many extra you got that you didn't actually need to get. And in that particular case, the L's did not get any extra. They needed 6. They got 6. So L wasted 0. All right? The next row, you just have to think this through for each row. It's not hard. You just have to make sure you know what you're thinking. All right? The next row is actually exactly the same, 4 and 6. So I am again going to say the D's wasted 4 because the loser wasted everything, and the L's wasted 0 because they needed 6 to win and they got exactly 6. All right? The next row is a little bit more interesting. Again, the D's lost. All votes for the loser are wasted, so the D wasted 2 in row 3 here. And then the L's got 8. This is 2 more than they needed, and so the L's wasted 2. That's because 8 is 2 more than 6. All right, and so on. What do we? Can someone say in the next row? How many is D wasted and how many is L wasted? I think you know. What do you say?
D wasted 0 and L wasted 4.
Yeah, great. D wasted 0. This is all votes for the loser are wasted, but it was 0, so D has wasted 0. And L got 10 votes. They only needed 6. That means 4 were wasted. All right, and then in the last row, it's actually the same, but the other way around. 4 here, 0 here. All right. What I see overall is D's have wasted more than the L's, which means that this map is favorable to the D's in that sense. Many of the voters who are trying to vote for D's, their votes didn't actually matter. Yeah?
Do you just then at the end count all the wasted votes together and then compare them?
Yeah, I'll say specifically, we're basically just going to add up how many each party wasted, and then there's a very, it's not complicated. I'll just tell you what you do, all right? So to finish, we basically done all the work here. Your final answer is a single number. It's a percentage. Is that a question?
For the last one, why is the D wasted 4 and not 10 if D lost?
For the last one, the D's won. It was 10 to 0.
Individual, not for the total. Right.
I'm not sure what you mean, but yeah, here the D's got 10. They needed 6 to win. So they did win, but they got 4 extra. And that's the 4 wasted. Yeah. All right, so we've done all the work. Essentially, we just have to sort of put everything together to find our answer. In order to do that, you add these columns. So in total, the D's wasted 14, and the L's in total wasted 6. So from there, you can say that this map is favorable to the L's, right? The D's are wasting more than the L's. But specifically how we report that is I suppose, very slightly complicated little deal. What you do is you also add up the total, which here is 50, and we say this is called the efficiency gap. The efficiency gap is, in this example, 14 minus 6 divided by 50. So what you see up top is the difference in the wasteds. The D's wasted more than the L's. How many more? This many more, like 8 more, right? And then you divide by 60. That's the total number of votes cast in the entire election. So this is 8 divided by 50. And that means of the total 50 votes, there were 8 more of them that were wasted for the D's than there were wasted for the L's, all right? This is the efficiency gap. And that's sort of if you're doing one of these problems on the test or something, that's your final answer. Now, typically in the real world, they write this as a percentage. So if you like, you can actually plug that into your calculator. This I did, and I got 0.16, which is 16%. All right, that's typically like if you read a news article about gerrymandering and they talk about the efficiency gap, which they often do, this is how they'll say it as a percentage. All right, so let me just say how specifically this little fraction that you get at the end. So the answer is always a fraction. Down here is the total of votes, right? You take that total column and you add them all up. That's the denominator of the fraction. And then the numerator is always something like the x wasted minus the y wasted. And you always do this. You take the one who wasted more and subtract the one who wasted less, just so that the numerator, you don't want a negative answer here. All right? And then the efficiency gap is this fraction, or this percentage if you like. And then you also say, so this is also part of the answer. Can I say, oh, I meant to say this before. And we say this is in favor of the L's. That's because in this example, the D's wasted more than the L's. So it's 16% in favor of the L's. That means this map gives a disadvantage to the D's. It gives an advantage to the L's because the L's wasted less, or the D's wasted more. The D's wasted more. All right. And you always need to say this as part of your answer when you say what the efficiency gap is. If you just say, the efficiency gap is 10%, I want to know, okay, 10% in favor of who? Like which of the two parties is being advantaged or disadvantaged? All right. This one was in favor of the L's because the D's wasted more. All right. You ready to try one? I got one for you all to try, and I have this picture on the handout. So this is actually two separate examples that I would like you to try. In each one, figure out the efficiency gap. This involves making that same chart and doing some simple adding up at the end. I'll scroll up to here. So in this example, the one on top is what I would say like a natural division into 4 districts, whereas the one on the bottom looks to me like it's been packed. It's using weird shapes and such. So you should expect that the efficiency gap on the bottom is bigger because there's more packing, and the one on the top should be smaller. But it'll take a while to work those out. See what you think. I will walk around and see how you're doing. Your chart should have 4 rows in it because you have 4 districts. Yeah, so
it would be different, right?
yeah, you always subtract it so that the bigger one is the smaller one.
Okay, so
As
it's
you
always the
know.
big number, always.
Yeah. This is all supposed to be positive, so.
Okay.
Minus this one. Okay. You're. Good. Yeah, that's good.
Yes. Yes, that first one is zero. Yes.
All right. Okay. Good, good. All right. Yeah. Thresholds. Try to do that.
Yes.
Get somewhere. Still good? Good. Still good? So every vote for certain places. Any votes beyond the threshold. So these are votes. So the rule is, I think it may be better. So this way, these got exactly how many thresholds. This has, it has lost in every vote for the every vote. Well, so the efficiency gap, when you do this thing, you get 0. Zero, but the answer is 0. That's what happens when you get tied. All good? Yeah, that's good. I'm going to write out what I got for these. It looks like everybody's doing good. All right, can we talk about these? I know some people are still going, and that's fine. It's a little. It'll take you a few minutes to do these. You got to count up carefully. But anyway, when you do the first one, like I said before, in my opinion, the first one looks like a much more natural division into even districts, whereas the second one looks like there has been some effort to pack them in. And I'm the one who made these examples. I will be honest with you. I did try to pack the darks into District 1. And you can, whereas the others are more evenly spaced, but I packed them into District 1. Anyway, let's see. In the first one, I hope that you got numbers like this. They were 9s and 7s when you count them up, and then the thresholds here are 9 in each case. And so, for example, in the first row, I said D wasted 0, L wasted 7. That's because D was the winner here, and in fact, they won with exactly equal to the threshold. So they got no extra votes, no wasted votes for the D's. L's wasted 7 because that's just part of the definition of wasted. Means wasted is every vote for the loser is wasted, right? And then for the winner, it's every vote beyond the threshold. So the L's wasted 7 in the first row. I hope that that's what everybody got. It seemed like as I was walking along. The second row is exactly the same as the first row, 9 and 7, and so the D's wasted 0, the L's wasted 7. And then the other rows are the same but the other way around. The D's wasted 7, the L's wasted 0. All right? And so for my final answer, I would add these and these. I get 14 here, 14 here. Also add the total. That is the total number of votes overall. And then I make the fraction. This is not very interesting in this example, but the fraction, I would say the efficiency gap is, actually, if you want to sound fancy about it, use an equal sign. 14 minus 14 divided by 64, which is 0%. All right? That indicates divisions which are, from the point of view of the efficiency gap, they are totally fair. No evidence of packing at all. All right? Of course, in the real world, it doesn't really mean that they definitely are fair, but according to this particular measure, these are fair districts. All right? And I don't say in favor of anybody, because this is not in favor of anybody. Everybody good with that example? I hope so. All right. Yes?
Couldn't you see before the whole process that it is clear that it is 0%?
I don't know.
If you just count them together, you can see it, and then is this whole process in the exam still do we still have to do it, or can we just say there is 0%, so there's no favor?
I'm not sure. How can you look at this and tell it's going to be 0?
No, if you just see that it's 7 on both
Oh,
sides.
from once you do this much?
Yeah.
Yeah, sure. Then you can, if you already notice at this point it's going to end up being 0, that's fine. Yeah. I don't think you can look at the original picture and tell immediately, unless you are better than I am, which is fine. Okay, can we try the second one there? Now, you have to count up a bunch of stuff for the other example. Maybe I'll just drag it down here. You have to count them all up to begin with, which is a little annoying. So in district 1, 2, 3, 4, I got the D's and the L's. Could somebody just tell me what do you get for the D's? Just read them down the column so I don't have to count them up.
14, 7, 6, 5.
Anybody agree?
Yeah.
Yes? Okay, and then the L's, they add to 16 each time, so I can impress you with my skills. That must be what the L's are. All right, once you have counted them all up, you don't care about the picture anymore. It's just a matter of analyzing the numbers. This is a bit more interesting example. Anyway, the total is still tote. I meant to write total, but I wrote tote. It's still 16 every time, and so the threshold is still 9 every time, just like the previous example. All right, and now this is the important part. The D wasted and the L wasted. So I'm going to circle the winners each time just so that it helps me keep track of it all. In the first line, I see 14 for the D's. They are the winners. That's 5 extra beyond the threshold. So I get 5 D wasted, and L being the losers, everything for the loser is wasted, so that's a 2. The next line is a 7 and a 9. Actually, this is the same as the previous example. It's going to be 7 and 0. The District 3, 6 and 10, that's going to be 6 for the loser, are all wasted, and then 10 for the winner. That's one more than the threshold, so that's a 6 and a 1. And then the last row is 5 and 11. The loser is 5, so that's 5 wasted, and the 11 is 2 more than the threshold. That's a 2. All right, I hope that you got those same numbers. Any questions about those? This is the hard part, I suppose. Now we just add everything up and report the answer properly. So adding up the L's is 5. Adding up the D's is 23, I believe. And then we also add up the total, which is 64 here. And so I say the efficiency gap is 23 minus 5 over 64. That, if you do the subtraction, is 18 over 64. I might ask you on the homework to write this as a percentage, but on a test or something, unless you have a calculator, I would expect you to just leave it like that. I don't care if you reduce the fraction. You can reduce the fraction in this case. I don't care. All right? But you should say this part. In favor of, is this benefiting the D's or the L's? The D's wasted more, so this is benefiting the L's. That's how you should think about it. All right? The D's have wasted more, so this is 18 over 64 in favor of the L's. All right? This is how we do it. Any questions about that? I thought we should try at least one sort of real-world example. Now, this is a real-world example, what I'm about to show you, although I'm going to say there are some reasons why it's not particularly realistic, but let's find the efficiency gap for the Connecticut representatives in 2020. This is the most recent numbers that I found when I tried to look this up. Remember, the U.S. Congress from Connecticut has 5 districts. And I looked up the numbers for these. So we have districts 1, 2, 3, 4, and 5. And I have looked up in the 2020 election how many votes in each district went for the Democrats versus the Republicans. I am rounding these to the nearest thousands. So in District 1, these numbers you just have to look up, or they would be given to you on a test or something. I might have on our tests or whatever, I might not even show you the picture of something, but just tell you a bunch of voting results. So for the Connecticut U.S. Congress representatives, District 1, the votes were like that. District 2, the votes went 218 for the D's, 140 for the R's. District 3, they went 203 for the D's and 138 for the R's. District 4, it was 224 and 131. And District 5, it was 192 and 152. All right. The D's won every time, which, we've already talked about that. In the state of Connecticut, all of our representatives are D's. And District 5 is the one where it was closest, but no luck for the R's in the state of Connecticut. Okay, let's see if we can complete the table now. Just because these are real-world numbers, the chart is going to be slightly more complicated than the made-up examples from before. If you're doing one like this, there's one on the homework that's kind of like this. You should use a calculator if you want to do all of these additions and whatever. Anyway, the total is I just add these two columns, and it's going to be slightly different every time, which makes this a little more interesting. So 223 plus 122, that is 345, I believe. Next row, 218 plus 140, that's 258. I'm pretty good at adding numbers as long as I don't have to carry. I don't like that carrying. 203 plus 138 is 241. I carried. 224 plus 131 is 355. And then 192 plus 152, I don't like the looks of that. 344, I think. I wrote it on my paper. Come on now. 344. All right. So those are the totals. Now we need to, in each row, the totals are slightly different. In each row, did I write 200s? These should be 300s. I was bragging about how good an adder I am. I'm not a good adder. All right? You all knew that. What about the thresholds then? The threshold will be half plus 1. Or if it's odd, you do half and then round it up. All right? So 345, I do half of that is 172.5, isn't it? And so I round that up. I get 173 for the threshold in that particular district. All right? So if all of these thresholds will be computed by dividing the total by 2. And then if it's odd, you round it up. If it's even, you add 1. So 358 divided by 2, I believe is I think this is 179. And I add 1, I get 180. Is that right? Anybody care to correct me? I think that's right. 341 divided by 2 is 170. And then I round up to 171. 355, I got 178 on my paper. 178 times 2 would be 356. That's right. And then 344, I put 172 on my paper. All right? Those are the thresholds. This is not really hard. It's just like numerically slightly more complicated. You just have to figure out half of those numbers and then round them up. Yes?
Is it 1 greater than half?
It's 1 greater than half, but sometimes half will be like a 0.5, and in that case you round it up. You don't add 1 to it.
Okay.
Right? You don't look pleased with that answer.
No, I didn't.
Yes, it should be 1 more than half, or half and then you round it up.
Would 172 be 173? Or is that 172?
It should be 173. Yeah, you're right. That's why she didn't like it. Yeah, thank you for that. All right, maybe I shouldn't attempt to do examples like this, which are beyond my arithmetical capabilities. It's fine. I'm a real mathematician. I don't sit around dividing numbers by 2 all day. Anyway, the rest I can do fairly easily. The D-wasteds, all right? So the D's 1 here. How many did they get beyond the threshold? The threshold was 173. They got 223. I believe that's 50 extra. And so the D wasted is 50. You subtract those numbers, right? 223 minus 173 is 50. I hope I did that right. And then the R wasted. What's the R wasted there? Shout it out. 122, yeah. All votes for the loser are wasted. So the R wasted is 122. In fact, I know the R's lost every time, so they are always going to just copy their numbers over for the wasted. All right. How many did the D's waste in the other settings? So here I have 218 versus 180. So I'm really, if you're using a calculator, you go 218 minus 180, which is 38, I think. Here I have 203 minus 171, which I believe is 32. Here I have 224 minus 178 is 46, I think. And then finally 192 minus 173 is 21. All right. These are the D-wasteds and the R-wasteds. And now we're done with the work, really, although we just have to sort of add things up and divide things out. So here I added these up on my paper. I hope that this number is still correct. I got 187, and when I added the R wasted on my paper, I got 683. And the total, I got 1743. All right. And so my final answer is, the efficiency gap is, I make that fraction. Up top is always these two numbers, the bigger minus the smaller. So it's 683 minus 187, dividing by the total, 1743. All right. This, if you do the subtraction, is 498, I think. And down here is, oh, it's the same. Copying from my paper. All right, this is about 28% if you do the division. All right. this is the efficiency gap. Yeah.
On the test, do you want us to do like the percent or
No.
leave it as a fraction?
Yeah, you should leave it as a fraction because you're not going to have a calculator. So don't do the percent unless you really want to. All right. Can I just say a few words about this in the real world? So this is a real example. Like I actually looked these numbers up. These are the real numbers. But this efficiency gap is super big. Actually, in the real world, this would be regarded as extremely unfair. In the real world, a ballpark sort of rule of thumb is efficiency gap of like 5% or less is regarded as acceptable. The worst example is the state of Wisconsin map, which I showed you last time, and that one was 11%. That's the worst example anywhere in the country in situations where it makes sense. This would be regarded as a situation where it doesn't make a lot of sense to use the efficiency gap. So I'm going to say, like, that's, this mathematically is the correct answer, although it is not really statistically meaningful. So the efficiency gap is statistically useful. This is the thing about statistics, like you can do the math and get an answer, but that's not necessarily reflective of anything that real that you care about in the real world. So the efficiency gap is statistically useful when there are many districts and outcomes per district are varied. All right, these are both important in order for the efficiency gap to be meaningful. First of all, the business about many district, this is just a general fact about statistics overall, is that statistics for the most part are only reasonable if you have they call it a large sample size, right? If you're trying to like average some stuff in a meaningful way, you should probably have a lot of things to average from. Like if I averaged the average income of like your parents from students across the entire university, that's probably a meaningful statistic to use to get a sense for like how wealthy Fairfield students are. But if I only ask 3 people and I average their incomes, that's less meaningful. I mean, it's still, you can say mathematically what it is. You still get an answer, but that's not very meaningful. In the state of Connecticut, there's only 5 districts, which is not really very many in terms of getting a statistically meaningful answer. And then the other part, the outcomes per district are varied. You can see already, like in this example, if the D's are going to win every time, then automatically the R's will be wasting more than the D's every time, because every vote for the R's is going to be wasted. So in a situation where one party is going to win all of them, it kind of means that this whole way of measuring things is automatically going to be skewed towards the one party rather than the other. And that's not necessarily because the districts are unfair. It's just because the D's won every time. Yeah.
With states or where there's less districts, would it maybe be a higher percentage needed to show that it would be a problem? Like if
you could say that.
Losing every vote threshold by 1, it would be close to like 100%.
Yeah, right.
Then show something.
Yeah, maybe. As far as I know, and I'm actually not really an expert in the how this is used in the real world, I think they would just say we don't consider the efficiency gap when we have this few number of districts. The example I showed last time, the Wisconsin thing, that was 99 different districts, and some of them were won by Republicans, some by Democrats. At that level, that's regarded as appropriate for using the efficiency gap. Yeah, there may be some things that you can say here. You would probably use some different kind of statistical analysis would be more appropriate than the efficiency gap here. All right, great. I think this is all that we need to really say about the efficiency gap. It's not so hard to do if you know what you're doing. You'll have some practice on the homework. This has been, I had a great quote that I wanted to share from you. The efficiency gap has been used at the United States Supreme Court in order to try to convince the Supreme Court to strike down some maps which were viewed as very unfair. So the efficiency gap at the U.S. Supreme Court actually was not, this happened within the last few years. Somebody tried to argue a Supreme Court case, and they said that this map should be declared to be illegal because it's unfair. And how exactly they described how unfair it was is they used the efficiency gap. And this means they had to stand there and like explain to Clarence Thomas how you do all this stuff. They had to explain, like, this is what the efficiency gap is, this is how you do it, and since we got this number at the end, that means that this is unfair. And the Chief Justice John Roberts, Chief Justice of the United States Supreme Court, John Roberts referred to this analysis as gobbledygook. Apparently he was not convinced by all of the math. I think this is something that I encounter in my own life sometimes. Every so often, you know, when I meet people at the club or whatever, they ask me what I do, and I say I'm a mathematician. And they ask me like, oh yeah, what kind of math do you do? And this is like a something that I've learned over the years is it's a delicate question to answer, because if I say something too specific, they will stop listening to me after a few seconds, and then they will get bored with me and they don't want to talk to me anymore. So I try to sort of gauge what I know about this person. What is the kind of thing that they will want me to say? And then I try to say something that will be understandable. And sometimes I say things that are not quite accurate, just so that they will understand me better. I don't know if you have ever had this kind of experience. But anyway, they misjudged Mr. John Roberts. This is my interpretation. They probably should have explained less to him, and he might have felt like he understood it better. Instead, they tried to explain everything, and he was like, I'm not into that. And so he did not respect their mathematical arguments. I don't think it's that complicated. I mean, it is like, if you walked in now and weren't sitting here from the beginning, you will look at this and say, what is that nonsense? It's not really that complicated. It's just, it seems complicated if you're not used to it. All right, that's the efficiency gap. So this is the first out of 3 actually methods that we're going to use to try to judge maps to see if they are fair or not. And the efficiency gap is this kind of statistical method. What I would like to talk about, and we can start, we got 20 more minutes today, we can start talking about this now. I would like to talk about 2 purely geometric measures of how weird the shapes are. This is usually the principal objection to an unfair map. You can tell that some funny business is going on because they're using crazy shapes in the map, all right? And so this is another way that you can try to measure how fair the map is just by measuring how insane the shapes are. Are they normal looking shapes like a circle or a square or something? Or are they some kind of crazy wormy things, all right? And that's where we're going with this one. And we have actually 2 different ways of measuring how weird the shapes are. And we can talk about one of them today. Maybe we'll start talking about one of them today. So the idea here is you don't even look at the voters at all. You just look at the shapes. And weird shapes are suspicious. A little sus, as the kids say these days. This is what my kids say. So how weird the shapes are, what I mean by that is something sort of like this. This one I would view as not so weird. All right. If I see on the map shapes that look like that, that to me looks like a reasonable kind of a shape versus something that's sort of like this. That is very weird. All right. And we would like some kind of way to tell the difference. Now, it's not just good enough for me to say like this one over here is pretty sus, am I right? You need some kind of actual measurement. So what we're going to talk about are a real sort of mathematical measure of sort of weirdness of a shape or wiggliness, right? And it's mostly simple geometry, although I'm pretty sure you never talked about something like this in your high school math classes. But you could have. It's not super complicated. All right, we want specific mathematical measure. I should say measures, because actually there's more than one way to do this, of course, and we're going to talk about two different ways to measure the weirdness or the wiggly worminess of a shape. All right. And they have cute names too. The first one, and this is the one we're going to start talking about today, is called the convex hull ratio. And then the second one has this fancy name, the isoperimetric quotient. You can impress your friends. These are the two measures of how weird the shape are, and you'll see those like on your checklist for topics. The convex hull ratio and the isoperimetric quotient are two different things. In both cases, what we end up with is like a percentage or a number. You could think of a decimal between 0 and 1, where 100% represents like a perfectly nice shape, very nice. 0% would mean like some kind of insane wormy shape. All right, and it's a very specific number that you get at the end after analyzing one of these shapes. All right, let's talk for the next 15 minutes at least about the convex hull ratio. Convex hull ratio. All right, this is something which is based on a simple geometric construction called the convex hull. So let's talk about, you may have seen this word convex before in geometry. Convex. This is certain types of shapes. Some shapes are convex, some shapes are not convex. And what it means, I'll draw some examples. So a square is convex. A typical example of something which is not convex is like a crescent shape. This is not convex. And the word convex in geometry, it means, here's the definition of what convex means. A convex set is, I'll say a set is convex when, this sounds kind of complicated when you write it in words, but it's actually very simple to look at a shape and tell me if it's convex or not. A set is convex when the straight line connecting any 2 points lies entirely within the set. When I say set, I just mean like a shape. All right, when the straight line connecting any 2 points lies entirely within the set. So, for example, the square over there, if I just take 2 points, any 2 points inside the square, is it true that the straight line connecting those 2 points lies inside the square? The answer is yes, it is. The straight line from this point to that point lies entirely inside of the square. And that's true for any 2 points, no matter where you put the 2 points inside the square. You can always connect them with the straight line inside the square. So the square is convex. This crescent type shape is not convex. It's because I can take a point up here and a point down here, and the straight line connecting them goes outside. And so that's why that shape is not convex, because it has a straight line connecting them, which leaves the shape. Convex means the straight line between any 2 points lies entirely inside of the set. How about a circle? Is that convex or not? Show me the thumbs. You say convex or not. Thumbs up means any 2 points can be connected by a line which is entirely inside the circle. Or thumbs down. Everybody says thumbs up. Yes, this one is convex. Is convex because if I take 2 points inside the circle, no matter where, the line connecting them is still inside the circle. All right, so just some more simple examples. If I have sort of a hexagon-like shape, what do you think, convex or not? The answer is yes, that one is convex. How about my hand? I put an extra finger. I didn't mean to do that. Is that convex or not? This one is not, because if you take a point in one finger and the second point in a different finger, then the line connecting them leaves the set. So if I take one here and one over here, it goes outside. All right, so this one is not convex. This one is not. What else? I had a cute little guy there. This one also is not convex. All right. One way to think about is it convex or not, I would say, this is sort of a silly way of thinking about it, but I think it works for me. Maybe it will work for you. A convex one is a shape which kind of has no innies. The problem, what makes this not convex, is this like these sort of inward intrusions into the shape, the innies, if you will. If a shape, this circle has no innie bits, and so it is convex. If you ever have this sort of part which goes inwards, then it's not convex. And similarly over here, this one, you can do something like this, right? It's not convex because of that little innie right there. This is not convex. All right? That's how it goes, okay? So this is the difference between convex and not convex. I hope that everybody is clear on the distinction. What does this have to do with like wormy kind of things or whatever? I will just say most, real world shapes are not convex. What I mean by real world is sort of like, if you're walking along and you find like a rock on the ground, that is probably not convex. Even if it might be sort of mostly convex, like a lump of dirt or something might look like that. It's mostly convex, but it does have little innie bits around the edges, right? And so because of those, like for instance, right here, this little inwards bumpity bump makes it not convex right there, all right? Although you could say it's kind of pretty close to a convex, like it's if you just kind of rounded off all the edges, then it would be convex. Similarly, on the left side, I can see a little dip right here, a little dip, which makes this not convex because of that. All right, but I will just say this is sort of close to convex. Actually, if you take an ordinary shape, any shape at all. Any shape can be sort of, I will say, kind of filled in to make it convex by filling in those inward bumps by straight line segments. So any shape can be filled in to make it convex using straight line segments. I'll show you what I mean by that. All right, for example, if I have something like maybe this is not convex because of those three kind of inward facing bumps here, but I can fill it in by adding straight line segments across those dips. So I'm trying to do, on the upper left, I'm going to sort of add a single line like that and fill in this innie portion. So I can put a line right there, like so. Fill this in here. Then I can put another line over here. You can just find all the places where you have this sort of inward facing bumps and fill them in. Why is my line jumping? I don't want that. And then also across the bottom. Fill this in using straight lines. All right? What you get is a larger shape because you have to add stuff in to make this convex. So now, after I fill in the red stuff, now it is convex. And this new shape that I got, it comes from some old shape which I have added stuff to make a new shape. This new shape has a name. This is called the convex hull. Of the original shape. This is called the convex hull, all right? The new shape is convex. The original shape was not. The way you get the new shape is by filling in all the non-convex parts, by adding straight lines. All right. Another way of thinking about the convex hull, I usually think of it as like you fill in the innies until there's no more innies left. All right. Another way you could think about this is it's the same shape as if you wrap a rubber band around the original shape. That's another way of thinking about this shape that you get, which you might like that a little better. I don't know. Same as if you wrap a rubber band around the original shape and sort of let it stretch down as far as it can go. What you get is also it's the same. It's the convex hull. All right. So this is another way to think of what the convex hull means if you wrap around the original shape with a rubber band. All right. Anyway, that's the convex hull. For example, how about a Pac-Man like that? Let's say that's my original shape. This is not convex. Can you draw the convex hull? That is, you fill in the innie bits. Maybe I'll just copy this. So that one on the left is my original shape. To get the convex hull, you fill in the mouth. Basically, is the innie bit. I have to fill that in using a straight line segment. So I'm going to connect here to here, the jaws, and fill this part in. All right. So that's the original shape. That's the convex hull. It is what you get by filling in all the inward stuff. This is the convex hull. All right. Just a couple more simple examples of that. What if I had something that looks like the letter E? Or actually, let's talk about the letter F first. What's the convex hull of the F? You have to fill in all the innie bits of this F. Now, you have to kind of be sure that you get enough of it. You might think, well, I should just fill in that part right there, right? Because that's an innie part. But actually, there's still innie parts remaining on this shape. Can you say?
I would do it completely to the lowest point. I don't know.
Down here?
This one.
Yeah. Actually, if you want to fill in all of this inward bumpity bumps, there's still inward bumps here. You really have to go from here all the way down to there. Or you could think of the rubber band wrapping around this thing. The rubber band would not stretch all the way in there. It would end up straight across here. So actually, the proper convex hull is like that. All right? It's really this entire shape is now the convex hull. And what about the convex hull of the E? Can someone just describe in words what would the total shape look like if you filled in the E? Yeah?
A square?
Yeah, it would just look like a square or a rectangle, whatever that is. You would have to connect up all of that, and you get everything on the inside. All right? Just to make sure, this I think is an easy concept, but just to make sure that everybody is with it, I have a cute handout here with a bunch of weird shapes on it. Your job is just to scribble in the convex hull of each shape. When it comes to actually doing the convex hull ratio, it's a more complicated process that's based fundamentally on doing this to begin with. You got to make sure you got this straight. So for each of these things, just scribble in a few straight lines to make the convex hull.
Can there be multiple lines for one object?
Yes?
Okay.
Yes, you probably will have to add more than one line for each of these shapes. Scrutinize this guys really should go a bit further out because they're still If you know what you're doing, these are very easy indeed. Yeah. And the idea is for these shapes like this, they're the same. That's how it is, just the same as that. But for a wormy shape like this, that's all it is. It's much bigger than that. Yeah. So that's. All right, let's talk about these. It looks like everybody's doing great. So there's not a lot to say about it. If you know what you're doing, these are pretty easy. So the heart, you should connect across the top to fill in that part. Also, there's a little part over here that you should probably fill in, but I think that'll do it. Maybe on the left side, I don't know, if you're looking very carefully, you might want to fill in a few spots on the left side. For the star, you have to add in like this to turn it into this sort of Satan star, like so. It's a pentagon. This sort of wormy thing up there, you should connect up. Remember, I should be using straight lines to do this. Something like that, right? So that I get this whole region like that. I hope everybody's pictures are looking like this. This weird thing over here, you have to connect here and also here, like so. The house, you gotta do that and that, like so. The circle actually is already convex, and so when you try to add stuff in, there's nothing to add. So this shape right here is already equal to the convex hull. There's nothing to do. This one you add like this, and you get all of this. The triangle, again, is already convex, so you should not have added anything in here. And then this sort of smiley worm here, you connect like that. All right. Let me just tell you in our remaining 1 minute, what's the point of all of this business? The point is, I will have you notice, for a nice shape, the original is the same as the hull, the convex hull. But for a wormy thing like this one, for a wormy like that one, say, the convex hull is actually much bigger than what you started with, all right? What you started with is a narrow little wormy, but the convex hull ends up adding lots of area that didn't used to be there. So for a wormy, the convex hull is much bigger. And that's how it's called the convex hull ratio. You make a ratio, like a fraction, of the area of the thing you started with versus the area of the convex hull. And if they're pretty much the same, then you get a number that's pretty much like 1. If the convex hull is much bigger, then you get a number with a huge denominator, which is a small number. So here, the hull is much bigger. That's the point. We'll do the details of that next time, though. As you're leaving, I printed out the homework just because it has pictures on it.